start from battery cells, and then at the end, we'll scale everything up to battery packs. What I'm planning to do is to stay most of the time within the MATLAB and Simulink environment. What we are simulating here is single cell response to step current. What we are seeing here are three plots. The first plot is the current, the step current as the input to the battery cell. The second plot is how the temperature responds to that step current. The third plot is the voltage, how the voltage responds to it. The most recommended way of doing this is to go to the lab and do experiments, and then based on experimental data, we go through a procedure called parameter estimation.
I have the pleasure to host another deep dive session today, together with Xiangchun from MathWorks on the topic of advanced thermal modeling for battery systems. This deep dive session explores advanced modeling techniques for accurately simulating the coupled electrical and thermal behavior of single cells and battery packs under various conditions. So with that very, very short introduction out of the way, Xiangchun, the stage is yours.
Yep, thanks, Joseph. Hi, everybody. It's good to be with you again. My name is Xiangchun Zhang. I'm an application engineer at MathWorks. I help our customers understand how to use our tools on battery modeling and the BMS algorithm development. So today, like Joseph mentioned, I'm going to show you a few examples on how to perform battery modeling, especially the coupling between electrical and thermal behavior for batteries. And we will start from battery cells, and then at the end we'll scale everything up to battery packs. And so what I'm planning to do is to stay most of the time within the MATLAB and Simulink environment. And then there are some occasions I might refer back to my PowerPoint slides. So what I have here is a MATLAB project, and then it has three examples contained. So I'm going to open up the project, and then I'm going to show you three examples. The first example is a battery cell model. So in which case, we model how a single cell responds to a step current in its electrical and thermal behavior. So what I'm planning to do is that I'm first going to show you the results, explain to you what the results are, and then I'm planning to do to show you how to build the model from scratch from an empty Simulink canvas. So that's the plan for the first example and demo. All right. So what we are seeing here are the simulation results. As you saw, when I click the play button here, the simulation compiles and runs pretty fast, and then seconds. So what we are simulating here is a single cell response to a step current. Yusuf, can you see my screen? The font size okay?
I think we can slightly increase the font size. I think that makes sense.
Okay, let's see. Well, seems the scope, I don't have much option, but I will try to increase font size for other components. So I'm going to talk through it, and then assuming the font size is too small. Okay, so what we are seeing here are three plots. The first plot is a current, the step current as the input to the battery cell. The second plot is how the temperature responds to that step current. The third plot is the voltage, how the voltage responds to it. So if we look at the current input profile, at the beginning, we are doing a 27 amp discharge for the cell, and then 27 amp happens to be 1C discharge. The battery is rated at 27 amp hour, so 27 amp equals to 1C discharge. So C rate is a jargon in the battery industry. It's a normalized current we use to discharge our battery. For 27 amp hour cell, if I use 27 amp, that's 1C. At t equals to 400 seconds, the current is turned off to be 0. And then meaning we are no longer drawing the current from the battery, and then we are observing how the battery would respond when the current goes from 1C to 0. And the bottom plot is how the voltage responds to this kind of step current. At the beginning, since we are discharging the battery at 1C, so naturally the battery voltage would gradually decrease in a nonlinear fashion. And then the moment we turn off the current, the battery voltage would first have an instantaneous recovery and then a gradual recovery. The instantaneous recovery has to do with the electron conduction and then direct current internal resistance inside the batteries. And the gradual recovery has to do with the fact that lithium ions, they take time to diffuse in the battery components, especially the solid phase active materials. And that's why we are seeing a gradual recovery. And in terms of temperature, the middle plot, when we are discharging the battery at 1C, we are generating heat inside the battery cell. And then when the heat generation surpasses how fast the heat is being dissipated to the environment, the temperature would gradually increase. Okay, when we turn off the current, we no longer have that internal heat generation source term, then we are only dissipating heat away to the environment. So the temperature would gradually decrease. And I haven't simulated it long enough. I stopped the simulation at t equal to 600 seconds, but if you simulate long enough, the temperature would gradually asymptote to the environmental temperature. Okay, so I think it's a simple enough a case and then a profile we can simulate. But I thought it would be interesting to look at how we can look at this example and understand how we can build a thermal and electrical coupled model using Simscape and Simscape battery. And I'm going to close the model and then say I'm going to build this from scratch. And then don't worry about everything here on the screen. I'm going to build everything from scratch, and then we can talk through it. Okay. So I'm going to open up a blank Simulink canvas. And then, so for those of you who are not familiar with Simulink or Simscape, and then Simulink is a block diagram modeling environment, and we model systems using block diagrams. And we design controls algorithms using block diagrams in the Simulink environment. And in the Simulink environment, we can also use Simscape blocks, and Simscape is good for modeling coupled multi-domain physical systems, such as our battery systems. We talk about, say, battery behavior is highly coupled between electrical and thermal aspects. So to build a model to achieve the thing, the example we just saw, so the first thing we do is that we bring a battery cell block. So typically we double click any empty space on the canvas. We can start typing here, say, battery. So there's a list of battery blocks we want to use, we can use. And so I'm going to choose battery equivalent circuit block. So battery equivalent circuit models battery electrical behavior using an equivalent circuit model, or ECM, and then models battery thermal behavior, either use a lumped thermal model or a height distributed thermal mass model. We'll talk about more of those in a little bit. And if we open this block, I will say I want to do a lumped thermal mass, and then it will expose another thermal port, which we will build a thermal network to model the heat transfer of the heat generation from the cell to the environment. So now this is our cell block. Okay, and then we need another block to describe how fast or current, how much current you want to run through the battery cell in terms of discharge and charge. So I'm going to bring another block called controlled current source. And then this is another Simscape block. And it is very useful to use this kind of block to describe how much current I want to use to discharge and charge the battery. In other words, how much current, what is the current profile I want to cycle the battery. So it's going to be a current-based profile. So like I mentioned, in Simulink, it's a block diagram modeling environment. And then we are using Simscape components. So we're just going to connect things just as if we are constructing an electrical circuit. So I have a current source here, I have a battery here, they are all connected. And then like any electrical circuit, we need an electrical reference. So I'm going to bring an electrical reference, and then so I'm going to connect the electrical reference to the negative terminal of my battery cell. Now, you might ask, say, controlled current source, how do I define how much current? Like the example we saw earlier is a step current. How do I define a step current? Well, so one way of doing it is that I'm going to bring a physical signal called the PS step. And then I'm using this physical signal generator. I can define a physical signal that specifying how much current I want to run through the controlled current source, and then when I want to turn on and off the current. So I'm going to make the font size here bigger so it's more legible. And the way to do it is just to press Control and plus on your keyboard if you are practicing this along with me. So here, you can see step time. Well, let's do 400 seconds. So we will turn off the current at 400 seconds, and the initial value, or we'll do minus 27, and then the unit is amps, meaning within the initial 400 seconds, we are going to discharge the battery cell with a 27 amp current. In the SimScape battery convention, we use negative current for discharge. So therefore, initially is a minus 27 amp for discharge the battery cell for 400 seconds. And then once the time reaches 400 seconds, we'll turn off the current. The current will be 0 amps. So that's how we specify a step current as an input to the battery cell. Okay, and then now we have a complete circuit, but we haven't completed the thermal branch. So in this block, it keeps track of both electrical and thermal behavior. So that's the point I mentioned earlier about that. Say SimScape is great at doing multi-domain physical system modeling. So within one block, it deals with both electrical and thermal domain. And it does a pretty good job of coupling electrical and thermal domain, meaning how much heat is generated, calculated from the electrical domain, and then that heat generation used as a source term in the thermal domain. And then the thermal domain will evolve the temperature, and then temperature will affect the electrical domain properties. And then so therefore, there's a two-way coupling between electrical and thermal domain, all within this one block here. Okay. Now, let's draw a thermal network to describe how the heat is going to be dissipated from the battery cell to the environment. So I'm just going to draw a very simple one, and then as a starting point to say I have a convective heat transfer block. I'm convecting heat from the cell to the environment. And you can imagine that, say, I have a cell sitting inside maybe a temperature chamber, and then the air is flowing inside the temperature chamber, and then however heat is generated will be dissipated through the convective heat transfer block to the environment. Okay, and I'm just going to put keep the default environment temperature like 293 Kelvin, and then I'm going to change the heat transfer, convective heat transfer properties here. Say my area for convection, I would say let's call it 40 centimeter squares. And then the coefficient, let's say I have a very strong convection, forced convection, let's do 100. And then, so that's pretty much it. So we have constructed an electrical circuit, and then to describe how much current we want to run, then discharge the battery, and then we have constructed some very, very simple heat transfer network to describe how the heat is going to be dissipated to the environment. And so the next thing to do is that for any SimScape simulation, we want to set up the stop time. And then remember that the step time, the step change in current happens at 400 seconds. So we probably want to simulate longer than 400 seconds just to see that behavior when we turn off the current. So maybe we'll do 600. And then if we simulate it, and then you can see that, so it says that each physical network must be connected to exactly one solver configuration. So what this does, what this error message means is that this is something unique to SimScape, and then we always need to provide a solver configuration to every SimScape network. So don't worry too much about this. And then there are occasions we need to specify dedicated solvers for SimScape network, but in most of the battery applications, we don't have to worry about it. And then let's try to run this again. And then now everything runs. But then the question is, how do I visualize the simulation results? So now simulation has run to the stop time. There's no error, but I want to see the results, right? So we talked about at the beginning, the example, there was a scope where we can visualize the results. But the thing with scope is that the scope will only help us visualize Simulink signals. So we have a lot of SimScape stuff here. And then to to bring the simscape component simulation results out and then display on a scope. And then one of my preferred ways is to do a probe. Meaning we use a utility block provided by simscape called probe. And then just like we use a multimeter to probe the voltage across an element in the circuit, we double click the probe and then single click the battery. And then it will bring up a list of variables that we can probe within the block. And then these are variables that are being solved by the simscape and then Simulink, and then the variables that are accessible from the probe. So you can see here, it's a long list. So for this example, we are particularly interested in three things: battery current, battery temperature, battery voltage. So we are going to probe those three signals on understanding the battery temperature, voltage, and current. All right, so we have three signals we want to put on the scope. Then I'm going to make the scope larger, and then connect all the lines, and so we'll have three signals coming to the scope. And then it's always a good practice to name the signals, and then I'm going to say this one is current, I, and then unit is amp. This one is temperature, unit is Kelvin. This one is V, meaning voltage. Temperature is volt. Unit is volt. And then we can display it on the scope, and then we are going to change the scope to be a 3x1 layout. And now if I simulate again, we will be able to visualize the results on the scope. All right, so these are the plots we saw at the very beginning. And then the first one is a step current. The second one is the temperature response. The third one is how the voltage looks like. And then here you might ask, say, hey, your voltage looks different from before. Like, how come your voltage drops as a straight line and then you don't have that gradual recovery? So I'm glad someone might ask that question. So if we go to the block, we haven't talked about this block at all. Like right now, we are only using some of the default settings. And so to achieve the results we saw earlier, and then one thing we might do is that we go to the over potential section, and then we specify that, say, for example, I want to do a 1 RC dynamics. So I'll come back to this 1 RC, what it means in a moment, and then but I'm just going to set up, say, I want to use 1 RC dynamics, and then we'll run the simulation again, and then after that I will explain what 1 RC means. Okay, so let's simulate again, and then you will see that say now the voltage behaves nonlinear during discharge, and then there's a gradual recovery as well, just because we added that 1 RC. So what does that mean? Then to explain that, I'm going to bring up a slide, and then we can talk through it. All right, so what I have here is an equivalent circuit. So this is an equivalent circuit, a diagram, and what we are seeing here, like say, those two are the terminals, positive and negative. And then we can imagine that what I have enclosed with the red box is within my battery cell. Okay, so in this case, when we are talking about equivalent circuit model, we use an equivalent circuit to mimic the dynamics inside the battery. So what's really going on inside the lithium-ion battery is fairly complex. There's going to be lithium-ion diffusion in the solid active materials. There's going to be lithium-ion diffusion and conduction, or we call it migration within the liquid electrolyte. There's going to be electrochemical reaction at the solid and liquid interface. There's going to be a conduction of electrons in the solid materials, including conduction additives. And we in the previous session we talked about different levels of fidelity, equivalent circuit model and the electrochemical model. So here we are using an equivalent circuit, which is a relatively lower fidelity model, but it runs very fast. It's very suitable for system level simulation. It's also suitable for BMS algorithm development. And what we are seeing here is a diagram of an equivalent circuit, and then what's in the red box is you can consider it as inside the battery cell. We are using those circuit elements to mimic the dynamics. So what do we have here? We have an ideal battery. So that's describing how my battery open circuit changes over SOC and temperature. So open circuit voltage, meaning if I don't run any current in and out of the battery, if I use a multimeter to measure the battery voltage, what the voltage should read. So you can consider it's a signature and characteristic of the battery electrodes mostly. Then it has to do with the electromotive force of the battery's positive and negative electrode. It tends to be very SOC dependent. It has a slight dependency on temperature as well. So that's the open circuit. And then we use a few resistors and capacitors to mimic the battery dynamics. For a resistor R0 here, so this is mostly to mimic the elements or processes within a battery that when I have a current, there's going to be an instantaneous voltage drop. So sometimes we call this a series resistor or instantaneous resistor. It has to do with the direct current internal resistance mostly. And then we also have two pairs of RCs, so resistor and capacitor pair. So for those of you who might be familiar with some of the characteristics of a capacitor, you can imagine that the voltage across a capacitor, they don't change instantaneously. So there's always some kind of charge discharge dynamics associated with an electrical capacitor. So voltage does not change instantaneously across a capacitor. So we are using that characteristic of a capacitor to mimic certain processes within a lithium-ion battery, such as a diffusion process. So now in this example diagram, we have two of those, and then it is these two elements that has to do with those gradual voltage recovery when we turn off the current. The R0 is the instantaneous voltage recovery element we saw within when we turn off the current. So let's come back here, and then if you look at this side by side, so mostly we can attribute this instantaneous recovery to the R0 here. We can attribute this gradual recovery here to the RC circuit here. And then we assigned one RC in this model we have just built, so we don't have the second RC, but the gradual recovery is attributed to this. And then in terms of temperature model, so in this example, we are using a lumped thermal mass model. And then basically what it does is that the thermal mass multiplied by my temperature, time gradient, time derivative equals to how much heat is generated, how fast heat is dissipated to the environment. And then the heat generation term, there's two terms. There's a resistive heating and entropic heating. Resistive heating comes from the electrical element modeling, and then it is irreversible. The entropy heat is a term that has to do with the phase change inside the battery materials, and then it is proportional to current. And then this term is important when you are dealing with moderate to low rate applications. And now those two are the heat generation source term. The dissipation term is essentially your heat transfer network you draw to describe how fast the heat is being dissipated to the environment. And now with this equation, we can solve the temperature over time. And then with that information, we can update the RCs on the left-hand side because they depend on temperature. So this way we have like a two-way coupling. And then the good news is that it's all taken care of within this single block. So that's what we did earlier. And then that's what we saw in this model we built together. Okay. And then I think this is pretty much the first example I want to share with you, just to recap. And then in this first example, we modeled a single cell's response to a step current. We modeled both the electrical and thermal behavior. And then we talk about how we can build the model from scratch. We talk about the basic workings of an equivalent circuit and the lumped thermal mass model. And then we talk about how we can instrument the SimScape component signals by using a probe to display it on a scope. So Yusuf, do we have any questions from the audience at this point?
Very good question. We have one question so far. Can you simulate the rest phase voltage curve after discharge phase in a more practical manner? Because the instantaneous voltage rise is not vertical exactly in an experiment, and it often leads to not so practical results in drive cycle simulations. Very long question though.
Yeah. No, so that's a good question. So I think my interpretation of the question is that, say, the instantaneous voltage here. And then the question is about whether, like say, this is a realistic reflection of battery behavior. And then when we go to the lab, if we do the measurements, then do we really see a vertical line for the instantaneous voltage recovery? And then say, especially what it means for drive cycle simulation. So that's a good question. I think that there are a few things packed into this question. First of all, I think say the equivalent circuit here simplifies a lot of things, and then we talk about say the R0 will dictate that instantaneous voltage recovery, and so typically we need to specify parameters such as R0, and then the most say recommended way of doing this is to go to the lab and do experiments, and then based on experimental data, we go through a procedure called parameter estimation, or sometimes we call it an inverse problem, and then some people also call it cell characterization. Then we can estimate the parameters. So we would, based on the real-world experimental data, to estimate parameters such as R0, R1, and C1, and then we parameterize the model. Okay. So in other words, if you do a proper parameterization for your cell, you might not see as much instantaneous recovery. So that's number one. Number two is that for battery measurements and then in the lab, and then all the testers, there's a response time, and then typically it's about say about dozens of milliseconds, and also there's a like a smallest time step we can log data, measure data by the tester. So in a real world, I doubt that we can continuously log data in a time interval of say milliseconds for a regular battery tester. So that will be a very, very say expensive battery tester if you can measure data and log data over a time span of 1 millisecond. And so therefore, it might appear that when we measure the data, measure the cell's response to a step current in the lab, we might not see a very straight line. That has to do with how fast the tester can measure and log the data. So that's another element. So the third element of the question is, what does it mean for drive cycle simulation? So I think, the best thing we can do is that we use our experimental data to parameterize the ECM, and then we bring all the parameters here. So here I'm just using all the default parameters. So the recommended way is that we go to the lab, we do the experiments using parameter estimation. We get all the ECM parameters. We put those parameters here that would represent the cell we are working with. And after that, we can run a drive cycle simulation. So in that case, what we might do is that we still use a controlled current source, but we'll say, for example, from spreadsheet or from workspace, it's a Simulink signal which describes how the current would change over time for drive cycle. And then we bring the Simulink signal into this controlled current source. So in that case, we need to first convert the Simulink signal to a physical signal using a Simulink to PS converter. And then once we did that, we can connect this one. So if we want to simulate a drive cycle response, then that's how we do it. And drive cycle coming from a file, and then convert it to physical signal, and then we simulate it. And then the battery needs to be parameterized using the data we collected from the experiments that represents the cell we are working with. So it's a very good question. There are a lot of elements to that question. Thank you for that question.
Excellent, thanks, Xiangchun.
Yeah.
There's one more question. Does MATLAB have an option of DFN-based models?
Great question. So for the folks who are not familiar with this area, DFN meaning Doyle, Fuller, Newman, those are the initials of last names of three authors who pioneered a type of battery model called electrochemical model. Some people call it the pseudo 2D model or P2D. And what I want to say here is that two aspects. One is that a SimScape battery supports electrochemical model, which is a simplified version of DFN or P2D, or what we call like a single particle model with electrolyte dynamics or SPME. That is already supported by Simscape battery. And then in terms of DFN or P2D, we very much understand everybody's interest in this area, and then we are considering this in our future plan.
Excellent, Xiangchun.
Yep.
Okay, let's move on.
Okay, thanks. So great. So I'm going to close this. This is a model we built from scratch. So I'm not going to save it. And then this is my slide. Just move it to the side. And then let's see. Okay, so this is the first example. I'm then going to close it. Now let's do second example, right? So the second example, let me set the stage, right? So for the second example, like the problem statement is like this. Say, well, so it's all good, like non-thermal mass. So the example we just saw, we saw only one temperature then per cell. So one question would arise like this: say, hey, I have a cylindrical cell sitting on top of a cooling plate. So imagine this is my best drawing of a cylindrical cell, and then I'm not good at drawing, but let's just use this one, and then cylindrical cell sitting on a cooling plate, right? And then we are cycling the battery. So like we are drawing the current from the battery to drive on the highway of the electric vehicle. Then battery will get hot. And then there's a cooling plate, running coolant inside the cooling plate to carry the heat away from the battery cell. So remember the first example, we had a convective heat transfer block. That's the simplest heat transfer network. A more complex one will be a cooling plate with coolant running underneath, which we can do that as well in Simscape. But so in a simplified diagram, say I have cylindrical cell, cooling plate at the bottom to dissipate the heat from the cell to the coolant, and then eventually to the chiller. Okay, so in that case, well, non-thermal mass, is it a good enough fidelity? I would expect that if I have a cooling plate at the bottom temperature will be lower, top temperature will be higher. I would expect a temperature gradient within the cylindrical cell. So then the question is a non-thermal mass a reasonable, accurate model? What if I want higher fidelity, right? So to address that question, our development team, they provided the option of doing a height distributed thermal mass. So what this means is that we discretize the model or the cell along the height direction into a few nodes. So how many nodes? Well, that's an option we can choose. I would recommend you to do like a few. Don't try to do 100, and then that way we are doing FEA. So like a few nodes just to resolve that temperature gradient along the height direction a little bit, and then we can have the temperature gradient along the height direction better resolved. So by doing that, we are extending the resolution from lumped thermal mass to a height distributed thermal mass. So that's what the second example is going to be about. And move that out of the way. So example number 2, cell height distributed. So I'm going to open that. And then, so in the near future, you would have access to this kind of example as well. So you can follow along. Say when you open the project, there's a project shortcuts tab. Then if you want to practice the examples, you can just do what I just did. Click example number 2. It will open up the second example. So what second example does is very similar to the first example. So here I'm doing a constant current discharge. So current is at 1C. Okay. Constant current discharge. And now you can see that instead of doing lumped thermal mass, I'm choosing a height distributed thermal mass. So let me make the windows adjust properly. So is the font size about right, Yusuf, for this window?
That looks good, yes.
Yep. All right. So thermal model, and there's a few options. One is no temperature dependence. There's constant temperature. And constant temperature meaning we specify a simulation temperature. The temperature wouldn't change over time. There's a lumped thermal mass. That's the one we just used in the first example. The last one is the height distributed thermal mass. So that's what we are using here. And then we choose that. And then if we go to the thermal model section, and then we get to specify the battery thermal mass. We get to specify how many thermal models we want, meaning along the height direction, how many thermal nodes we want to discretize the thermal model into. So here we say 6. So that will provide 6 temperature along the height direction. And to model things appropriately, accurately, obviously, when we do this, we need to provide the thermal conductivity in the Z dimension, and then what the cross-section area is, because when we connect those thermal mass together, we also need to understand and model the heat conduction resistance in between the thermal nodes. And then cell height, of course, is required. And then the reversible heat, which is the entropy heat term we talked about earlier in the PowerPoint, by default is disabled, so we don't use it in this example. Okay, so that's how we specify the height distributed thermal mass. And then I have, the way I'm setting this model is that, say, the 6 thermal nodes are passed within this SIMScape signal and then to a thermal interface here. So the thermal interface here, what it does if we go inside is that the first thermal node will be exposed and connected to a heat transfer network. Imagine that that's the bottom of my cell, which will be connected to a convective heat transfer to the environment. So the bottom of the cell, that's the first thermal node, will be connected to a convection heat transfer. And then all the others, I'm just measuring the temperature and then put the temperature out as a simulating signal and then log it. Okay, so that's what this model is about. And so bottom cooled, and then the top there's no heat transfer. Okay, so if we simulate this, and then we will see that we'll get a temperature distribution. And then so again, this is a simulating simulating scope plot. So the way to read this kind of plots is that the vertical lines is my temperature, the horizontal line is my time. So we are describing how those 6 thermal node temperature changes over time. So therefore, we have 6 lines. Okay, and it kind of makes sense. The first one is closer to the cold plate or closer to my convective heat transfer block. So therefore, the temperature doesn't rise as much. The one at the top of the cell, which is further away from the bottom cooling, and then therefore the temperature rises the highest. And so the plot kind of qualitatively makes sense. And I mentioned that we log the signal here. So therefore, when the signal is logged and when we simulate it, we'll be able to, just give me 1 second. Yeah, sorry about that. I had a cough and then have a mild cold. Sorry. So when we log the data will be available for us to analyze from the MATLAB. So in the out, if you go to the out, there'll be logged signal, and then if you open it, there are a lot of data for us to do post process. So those are the time column. Those are the 6 temperature files. And then once we have that, we can do a lot of other things. So one thing we can do is that, as I showed in the example here, we can visualize that time series data, 6 temperatures. If we go to MATLAB environment, we can start building some kind of small 3D visualization with animation, right? So what that looks like eventually is that if I go to my PowerPoint, and then once we post-process that and visualize that, that's how it looks like. So now, because we divide the thermal mass into 6 thermal nodes along the height direction, within each thermal node, the temperature is uniform. So we have 6 temperature from the simulating SIMScape model. Now we just visualizing it. So we are seeing how that temperature changes over time along the height direction over time. And then it's a small animation we can create using the tools provided by MathWorks. In particular, we are using a PD toolbox visualization function. Then we are writing frames of plots to a video, and then save the video file. So that's what's going on in the script I just showed you a moment ago. So just to recap here, what we saw is that we have extended our lumped thermal mass model to a height distributed thermal mass model, just because sometimes, because of the cooling strategy we are implementing for the cells, we would expect a temperature gradient along the height direction. So in this case, we discretize the thermal nodes into 6 masses along the high direction. So we get 6 temperature, and then say, like I mentioned, we need to go easy on this, and then you can see the 6 simulates very fast. If you choose 600, probably it will take a longer time to simulate. This is not FEA, so we are discretizing this into thermal nodes, still in SimScape technology. So, but it will provide some kind of temperature resolution along the high direction. And with the simulated data, if we log it, then we can post-process it in MATLAB. There are a lot of great functionalities in MATLAB. And then if we use PD toolbox, we can visualize the data. We can write the data to visualization to video frames and save the video. And then we can put the video in a PowerPoint presentation for reporting purpose. And then, so that's the second example I share. Okay, so I think it's straightforward. Extension to a non-thermal model to hide distributed model. I'm going to, so I accidentally closed the PowerPoint, which I didn't mean to, but I'm going to close this second example, and then say just clear that, and then let's go to our project, and then let's talk about the third example. Okay. See, I think I accidentally closed my PowerPoint. I'm going to open it again because chances are I might still need to use it in a moment. So just open that up. So we have it available for us. So now the third one is we want to expand this model even further. And because that's very limited things we can do with a single cell, right? And then a single cell, we probably can power a phone and then power a watch. But if you want to power a vehicle and then even a laptop, we have to have a bunch of cells, right? So inevitably, the question we have to deal with is how do we model a battery pack or battery module? And then how do we especially model the coupled behavior between electrical and thermal from a battery module and pack perspective? So the good news is that SimScape battery makes the scaling process from a cell to module to pack very automatic and seamless. And it's a fully automated process that can help us quickly scale from cells to modules and to a pack. So if I borrow the slides and then just to talk about some of the concepts here in a little bit, just elaborate a little bit. So in SimScape battery, we have this feature called battery builder, and then it enables us to quickly scale from cells to modules to a pack. And what we do is that we define the objects one level at a time, and then we define the topology of how cells are connected within a module and pack. And then at the end, we call one function, and then that function will help us to generate a SimScape block that represents the battery pack that we just defined. So it's a fully automatic process, and then all we need to do is to tell the process how many cells I have are connected in parallel, how many of those parallel strings are connected in series, and so on and so forth, just to define the topology. And then we also need to tell the process whether my cell is a cylindrical, pouch, or prismatic. And then from the cell modeling architecture perspective, we can choose equivalent circuit model, like the one we just saw in the previous two examples. We can also choose electrochemical model, like a battery single particle block. And then we can also bring our custom cell blocks as well, as long as they are defined in SimScape. They have negative and positive conserving ports, and then they meet some very, very loose requirements. And then we can bring our custom cell block in SimScape as well. So now that's how we can quickly scale up. And then there's another concept I want to talk about before we go look at the example. So the other concept is very important. It's worth mentioning here. That's so-called a model resolution within this context of modeling battery packs. So imagine that, say, for certain systems, I might have a few thousand battery cells within my battery system, like a car. I might have, say, 5,000, 6,000 cylindrical cells. There are some other systems, I might have tens of thousands of cells, imagine a big container full of battery cells for energy storage for grid, right? So the question arises, say, okay, you have thousands of cells, and well, if we have one model per cell, and then is it realistic to simulate this kind of system? Then the question, say, is a very valid one. We have customers have these kind of questions all the time. So therefore, uh, what we have here is that we get to choose the resolution we want to define for when we model the battery packs. So at one end of the spectrum, we have a detailed model or detailed resolution. What that means is that we will have one model per cell. So each cell will get its own temperature and voltage. So the temperature and voltage will be resolved on the cell level. So this model will have the highest fidelity, but it might take longer time to compile and simulate. So imagine if you have tens of thousands of cells, okay? So you probably won't even compile, okay? And then at the other end of the spectrum, we have a lumped model resolution. What this means is that all the cells within the lump, so what I'm drawing here is a 4-cell lump in the orange box. Everything within the lump, we would have the same voltage, same temperature. So this is the least fidelity, but this kind of model will simulate very fast. Okay, and we also have something in the middle, like intermediate resolution called grouped. So this really enables us to specify the resolution in the regions where we think we might have the highest temperature gradient. So we only allocate resolution to the region we think will have the highest gradient, maybe in voltage or temperature. So by specifying these kind of things, we can really strike a balance between model fidelity and simulation speed. So this is another important concept I wanted to mention. And then just so you know, like say, typically when you see these kind of orange boxes, and then meaning one box is one model. So everything within that box, it has the same voltage and temperature. We don't differentiate, meaning we assume the cells within that box or lump has a uniform temperature and voltage. Okay, so that's a concept here about model resolution. All right, with that out of the way, let's look at the third example. So what I have here in the third example is a module cooling. So now we are adding more complexity. So what we are dealing here with is so 14S4P module. It's a small module made of 56 cells. And we have 4 cells connecting in parallel, that's 4P. And we have 14 of those parallel strings connected in series, so that's 14S. So therefore, it's a 56 cell connected in a fashion of 14S4P. And you might see that I have 3 orange boxes. That means when I define the model resolution, I chose a group strategy. And therefore, all the cells within each box, they will have the uniform temperature and voltage. But I do have some resolution here along this direction. And everything within the box should have its own temperature and the voltage. So if I simulate this model, I would expect 3 different voltages and temperature. So, okay, so that's a small module of 56 cells. And then what I'm simulating here is that I'm subjecting the small module to a highway drive cycle. So, so one question asked earlier about drive cycle simulation. So here, I'm subjecting the battery module to a highway drive cycle. I think this is probably one of the European highway drive cycle Artemis, and then so I'm just letting the model compile and then simulate. It doesn't take very long, and then I'm sharing my screen and then doing a live screen capture. So it's slower than usual, but it's still fast enough. So okay, so what we have here? So we have 6 plots. The top right is the highway drive cycle current for this small battery pack or module, if you call it. You can see most of the current, they are negative. Okay, and then so this is my 0 axis. Most of the time it's negative, meaning I'm driving, I'm accelerating, I'm cruising. There are some spikes of current which is positive, meaning charge. So that's when I hit the brakes to do regen braking, and then during regen braking, the battery packs will be charged. So we have mostly negative current for driving. We have some regen braking charge currents. So that's a highway drive cycle. And then the middle plot on the top is the battery pack's voltage in response to this current. So I'm simplifying things here. I'm calling this small module a battery pack, but your real world battery pack, probably the voltage is 400 volts, 800 volts for electric vehicle. But here it's a demonstration, it's an illustration. It's a 56 cell pack. Okay, so the pack voltage looks like this in response to the highway drive cycle current here. And the top left plot is the SOC. So you can see we have 3 lines. So for a short drive, 800 seconds on the highway, the pack SOC dropped from 100% to about 90%. Okay, the 3 lines they almost overlap. Okay, so meaning the 3 lines we don't see a lot of gradient in terms of SOC. Which kind of makes sense. Those 3 boxes, they are connected in series. So we don't expect large difference in SOC. And then because, like I mentioned, we defined the grouped strategy for the model resolution. We have 3 models. That's why we are seeing 3 SOC curves. And then if we move along, that's the battery temperature. So 3 temperature because we have a grouped model with 3 models. If you look at the temperature here, what's going on here is that at the beginning, I'm driving on the highway, battery system gets hot. And at a certain time, I have a manual controller here. Say, at this time, let's turn on the coolant flow. So at that time, I have a manual controller turn on the coolant flow because the coolant flow now is turned on. The heat generated from the battery will be carried away from the cooling plate by the coolant to the other systems, right? So therefore, once I turn on the coolant flow, the battery temperature drops, which is expected. So my controller here is manual. I just say turn on the coolant flow at this time, but in the real world system, there'll be a more sophisticated controller and then closed loop control mostly. And then the middle plot is how the cooling plate temperature looks like, which is understandable. And then the bottom right is how the cell level voltage looks like. And then again, there are 3 curves because our model is grouped resolutions and 3 models. So that's the simulation results here. If we go back to this model here, what do we have? We have a generated block out of the automatic battery builder process, and which I will show you a little bit in a moment how to quickly build a block like this that represents our 14S 4P. It's an automatic process. And then we have a current control current source to bring a highway drive cycle current. So from workspace, then it's a normalized current in C rate, and then multiplied by the total capacity of the battery pack, do a conversion to physical signal, and then now we have an electrical circuit. And then we use a controlled mass flow rate source, and then I have a manual controller, say at t equals to 300 seconds, turn on my coolant flow at 0.03 kilograms per second. Then this mass flow rate source would draw coolant from one reservoir into the battery pack, carry the heat away to another reservoir. Okay, there are 2 reservoirs here, but in your real world system, you don't have reservoirs, you have a cooling tank. So that way, you can replace the reservoirs with a tank that's storing coolant. Okay, so that's what this model is about. Now, I'm going to spend maybe like 1 or 2 minutes going through the process, how we build this kind of generated block that represents a 14S 4P. So if I come back to here, and then see, we have, okay, so there are 2 processes of building the battery block, and then generate the battery block that using the battery builder. One process is using an API, and where we write a MATLAB script to define the topology of the pack. The other is to do an app. So both of them, they are doing the exact same thing. So if you prefer doing API, you can use the left-hand side. If you prefer to use a GUI, you use the right-hand side. At the end of the process, we would have a generated block that represents the battery pack we want to design. So it's a fully automated process. All you need to do is to specify the pack topology. And then for the API process, you just say build battery pack. And then it will generate this block for you. And then using the battery pack object you defined. If you use the app, and then at the end, you just say create library, and then it will generate the Simscape block as well, representing the battery pack you just designed. Okay, so those are the two processes you can use. And then in the example we have here, we chose API method. Basically, we follow a template script, which is a recommended way of doing it. So you use this kind of a template script we have on our website in documentation. Grab one, then modifying it, and then build your own battery pack. Okay. So we first define a cell, and then we define that we have 4 cells connecting parallel, and then we build the parallel object, and then we say we have 14 of them connecting series, and then model resolution is in grouped, and then the grouping is 455, and then we build a module. And then we also include a cooling plate where the battery module is being cooled at the bottom. And then say last step, we call this function, and then we build the battery pack. And then by calling that, it generates a block like this, then we can use it. So within the folder here, you will see that there are some library blocks that are automatically generated. So this one represents the whole pack with all the signals instrumented. There's also a library blocks for the modules and parallel assemblies. Okay, so that's all I wanted to share about this module cooling. And then in this example, what we saw is that how we can quickly scale from cells to modules and to a pack, how we can simulate battery pack's response to a high rate drive cycle while the battery is being cooled by a cold plate. And then my controller here for the coolant is a manual controller. The coolant goes from one reservoir to another. Those can be easily extended using Simscape fluids to model real-world systems where you have a coolant tank, and then you can also use some of the BMS blocks for thermal management provided by Simscape battery to control the coolant flow rate for a closed loop control. So that's the third example I wanted to share with you. And then, so just to recap today, what we did, we went through 3 examples. We started with a very simple example, a cell level lumped thermal model. We modeled the coupled electrical and thermal behavior. The thermal is a lumped thermal mass. And then we extended that to a height distributed thermal model, because sometimes we do expect temperature gradient along the height direction. And then in the last example, we extended the whole thing to a battery pack level with a cooling plate, and then we simulate how that responds to a high rate drive cycle in both electrical and thermal behavior. So that's everything I have, and I wanted to share with you. So last thing, and then if you guys are interested, and then I would recommend you to check out. Say we have some free resources to get you started. There's a Simscape battery on-ramp, and then you can check it out. It's free, and then everybody can use it. And then if you have a battery, if you have a MATLAB or MathWorks.com account, you can just go to here. So it's called a Simscape battery on-ramp. It's free. It's available to everybody, and then here you can do some exercises, and then get your hands on some of the processes and then examples, and then with that, anything else, Yusuf?
I think that's it. I shared every relevant link so far, at least from this session, in the chat, and then we'll follow up anyway with an email or uploading it again to YouTube with all the relevant documents, videos, webinars, etc. for this type of model, I would say. Excellent, Xiangchun. Perfect timing. Thank you so much. Hopefully there will be a second part in the future. Thank you so much for attending today's deep dive, and I'll see you in the next one.
Thanks, everybody. Thank you, Yusuf.